sampling from high-dimensional posterior measures. Go ahead.
Thank you, Hamza. Yeah, I'm really happy to be here, to have the chance to present some recent work of mine, where I try to shed some light on an important topic in modern data science, namely how to generate samples from high-dimensional distributions and how sampling affects subsequent tasks such as the statistical inference or uncertainty quantification. And here we don't want to just look at any kind of such high-dimensional distribution, but rather at high-dimensional distributions arising from high-dimensional posterior distributions in Bayesian statistics, where it's essential to have access to good sampling algorithms because typically the posterior is not explicitly available in closed form. And so, so let's see what we do there. So let's begin by assuming that we're given some data set n coming from some distribution P sub theta naught, where theta naught is the unknown parameter. And for the purpose of this talk, we will assume that theta naught lies in some infinite dimensional or high dimensional space. And then the Bayesian approach to learning about this unknown parameter is to compute the posterior distribution with respect to some prior that we choose. And then using Bayes' theorem, this amounts to essentially reweighting the data in the form of the log likelihood with respect to the prior, which is here chosen as a Gaussian prior. And well, so now for fixed data, this is now a proper distribution on the set of parameters, but here for computation reasons restricted to a finite dimensional space. Okay, and then the aim of the game is now to use this posterior to do inference on the unknown parameter. And for instance, statistical theory then provides guarantees given properties of the likelihood or the prior, such that, for example, the posterior mean is close to the unknown parameter, at least in the regime where the sample size n and the dimension p tend to infinity over the same time. But now in practice, of course, we don't necessarily have, or we usually don't have access to this posterior in closed form because, as I said before, yeah, it's not available classically because, for instance, this normalization factor here is a high-dimensional integral and or infinite-dimensional integral and cannot be computed in feasible time usually, and so we are usually restricted to using some kind of sampling technique to approximate the posterior. But then if you approximate the posterior, it's not clear that if P is large, that you can actually do this efficiently, that you can sample efficiently and at the same time still satisfy the statistical goal of approximating the true parameter by the posterior. So the fundamental question is then, can you actually generate samples from the posterior for large dimensions P at a reasonable cost? Reasonable in the sense of depending polynomially on the dimension and also on other important parameters involved in the problem, such that you can then, for instance, with the sample mean, compute the posteriori mean, which is hopefully then close to the true parameter. Okay, so this is the question. And before I tell you what sampling algorithm we use here, I will first give you two examples for concrete statistical models that are interesting in this situation. So the first one, we assume that we are observing a forward map, some function g sub theta with additive noise, and the noise is here assumed to be Gaussian. And in this case, you're not interested in really estimating this direct problem, the g sub theta, but you're rather interested in inverting the map theta mapping to g sub theta. And to give you a concrete example, let's assume that g sub theta solves a PDE. For instance, here this elliptic PDE where the unknown is hidden in this conductivity, and you have this elliptic PDE with boundary conditions, and you're not really interested in the solution itself. In fact, you can, in many applications, measure the solution at many points in some domain, capital X, and then you're rather interested in estimating the conductivity. So this is an inverse problem. And then in this specific case, the posterior likelihood has a familiar form. Namely, you have here this least squares contrast and the prior as well. So now this is an object that you would also find if you want to optimize, for instance, maximize this likelihood. And then this would reduce to like a penalized likelihood estimation. But we know that optimization is difficult if the underlying function is not convex, or in this case concave. And this is indeed the case in this specific PDE example, because the function, the forward map G sub theta, is nonlinear. You can show this in a specific context. So even though the PDE is linear, but the solution depends nonlinearly on theta. And so in this case, the contrast, the least squares contrast, will not be concave. And you cannot expect to find even optimizing in an easy way in this nonlinear problem to have the solution. And so and then especially also in the sampling context, it's not clear how this can. I assume that I want to that I'm given labels yi, features xi, and I want to predict the label for y given the covariance. And if you assume that this class probability can be written as after transformation as a linear function of the parameters and the features, then this is called logistic regression. It's a very popular classification algorithm in practice. And in this specific case, the posterior likelihood takes this form. So now you don't have a least squares contrast, but you're still nonlinear. This is still important. And in this case of a generalized linear model, this is one example, you actually are still concave in the likelihood, but it's not strongly concave. This is important here. So in fact, the practitioner might say, well, I add the prior to concavify my problem, but this turns out to be not enough. When you have a large sample limit, in fact, the prior will disappear. This is a feature of Bayesian statistics. Move on. Popular way to sample from a posterior distribution is to use Langevin MCMC. It's a gradient-based procedure where you define a Markov chain, which adds in every iteration step a gradient step with some step size gamma, and also a Gaussian innovation term with step size square root 2 gamma. And so this is easy to implement, right? It's just have to compute gradients. And you can show that in the continuous time analog, where the step size converges to 0, that the distribution of this process then for large times actually looks very similar or converges to our original distribution that we started with. But now, of course, when you discretize, you cannot expect that this still holds, especially not in high dimensions. And also, it's of course also expensive to do this, but nevertheless, it has been shown that in surprisingly recent papers that you can understand the mixing time of this Markov chain in the sense that the distribution of my output, the Markov chain, is close to the posterior in some sense that has to be quantified after just a number of steps k, which depend polynomially on the important parameters in the problem, in particular the dimension. So, but this is only true when the posterior is log concave. So this is not always true. In fact, you can show that if you're not log concave, then you will have generally exponential mixing times, and this would be quite useless then in practice if the dimension is large. But even worse for us, the posterior is generally not strongly log concave. So for instance, as I explained in my PDE example, when I have the least squares contrast and my forward map is nonlinear, then I cannot expect to have polynomial. As I said, an example where you can actually look up that the time is generally exponential in cases that you can find in a. All right. So what can you do now? Now, in a way, we are stuck. We have non-concave criterion functions. We want to sample. And so you have to exploit some additional structure that is coming from the statistical properties of my posterior measure. And there are two ideas here which are relevant. which I will quickly explain to you. So the first one is actually we are in a nice situation that we're looking at a nice statistical model. Yeah? So we have this, we have the likelihood, and in a regular statistical model, you have a sense of information described by the Fisher information. So when you evaluate the expected negative Hessian of the likelihood at the true parameter, then that would be called the Fisher information. And the Fisher information is, in a way, a sense of curvature in statistics, where you want to have large curvature to have high information. And in effect, having positive or large Fisher information relates to the fact that maximum likelihood is actually a good procedure in practice, which is exactly this property. You have curvature at a true value. And now if you perturb a little bit and you go away from this true value of theta naught, then you still expect to have some curvature. In a way, around the truth, in average, you expect to have some curvature, in average at least. This is the first idea. And the second idea is that when you look at the posterior itself, then there's a very nice statistical theory coming from the spatial non-parametrics, highly advocated by Boschel and van der Vaart, that shows that the posterior is not just an arbitrary measure, but in fact it contracts around the truth at a specific rate at the end, which tends to 0. And so in a way, the posterior puts most of its mass near the truth, in small balls around this truth. And in fact, the set where the posterior contracts is typically much smaller than the set of concavity that we of curvature that we have up here. So in a way, you can expect that at least close to the set of parameters for large sample, that's the criterion function. Our log likelihood, posterior log likelihood, is actually strongly concave on this set. Okay, so this is somehow to hope. Still heuristics at this point, but at least there's a chance that we actually living in a good regime where we can run MC. But now to use the theory that I described before, where we said MCMC has polynomial mixing times, we have to actually modify the likelihood because it's still not globally concave. It's somehow on most of the sample space of the space of parameters. It is concave, but not everywhere. So in order to use the theory from before, we modify it a little bit and we define something which we call a modified surrogate posterior likelihood, where we say we take notice like tilde likelihood, which somehow on a large ball around the truth looks like the original likelihood, and then outside of that we just brutally concavify in a way, which is and now why would that work? Well, this is somehow then where the math comes in. You can show that under mild assumptions on the model likelihood, and for moderate dimensions p, we have a high probability that actually this constructed surrogate posterior is close to the true posterior, and it's in fact exponentially close. This is under the like for fixed data in a way, with high probability. This from a practical point of view is that this surrogate likelihood is now log concave, so we can use the theory that was derived for log concave measures, but it's a non-Gaussian approximation. So usually numerical analysts or practitioners, they would do something like a Laplace approximation of the posterior, but in fact this is not a Laplace approximation. But it's good enough for, this is exactly what we want in this case. And then the idea is now to run MCMC not with the original likelihood, but with the surrogate likelihood, which locally you have a nice theorem which tells you that under the same assumptions that I had above, there exists now for every precision level a sampling algorithm, precisely here this surrogate MCMC, such that with polynomial cost, the output of this sampling algorithm computes or approximates the posterior in precision. So again, the important point is this is now a polynomial time guarantee. It does not really say that this is a good algorithm now, because I mean this is still a big O constant. a big O expression, so there could be large constants in there, but at least it says that principle, we can write down an algorithm that compute this in polynomial. That's this result and the previous one there based on work by Richard Nicol and his Wang, and also was extended in a and Richard, but somehow generalizes their conditions significantly to general likelihood. And then in the very end, the point is we don't want to just say that we can approximate the posterior, but we can actually also approximate now the true parameter theta naught by looking at samples. So now to wrap up, I want to just say quickly what is now happening with these examples that we started with. First in the least squares example with our PDE problem. What do we have to check here to make this work? Well, there are two conditions. One was to have curvature locally, and the second one was to have posterior. For curvature, we just get it reduces to studying some gradient stability estimate for the forward map, which you can, it's not trivial in the PDE examples because you actually have to use proper PDE theory to write these estimates. And this is then also attached to the specific PDE. There's no generic solution to this, but at least in principle it's possible. So if you have a favorite PDE in mind, you can sit down, work for 20 pages, and then you can derive this. And then one point here is also that, as I said, so this is curvature coming from the likelihood, but the prior in fact does not contribute to the likelihood asymptotically, because in order to make this work, to make Bayesian machinery work, the prior has to be scaled such that asymptotically it actually vanishes. This is a key feature of Bayesian statistics, that the prior washes out asymptotically. And so in fact, you cannot just take the prior to generate a cavity. You have to from the likelihood. And then in terms of posterior contraction, there are like a number of recent results for these nonlinear settings, especially for PDE studied here in Cambridge. So the theory applies to this, and for the logistic regression example, similar. Here it's a bit nicer because the likelihood itself is already like globally concave, but it's not strongly concave. In fact, you have on any fixed bounded set, you have curvature, and because also here the prior does not add anything to the curvature, you have to be careful. But this also turns out to work. You have curvature on any contraction is something that you go analogous to. Now to finish up, so in a way these are results that are somehow new in the sense that these are first statistical and computational guarantees for this problem. And to actually do posterior-based inference in this general non-parametric framework. A wide range of problems covers linear, nonlinear inverse problems with PDEs, or not with PDEs. It covers GLMs, generalized linear models, like logistic regression, and you can also use it in density estimation or general non-parametric. Next is you have this log concave approximation of the posterior in Wasserstein distance. To other sampling algorithms, so there's of course a lot more out there. MCMC is or Langevin dynamics is a very widely studied topic. And just to compare it to one algorithm by Harris with Vollmer, which works actually in the infinite dimension setting, it seems to be difficult to. So the nice thing about this algorithm here presented is that you have it's based it's n preconditions Craig Nicholson, and the point is there you have actually conditions which are independent of the dimension. So you get somehow nice conditions for infinite dimensional problems, but it turns out that when you really apply this to the concrete setting and you want to have finite sample guarantees, then you will still have dependencies on relevant quantities in particular dimension. And so this is not, at least it seems not easy to actually derive this, to derive results for guarantees in our setting. Open at this point. I didn't talk about initialization, so someone could definitely wonder, like, how do you initialize all these like Langevin schemes? And you have to sit down for each specific example and prove that there exists a computable initializer. This is not trivial as well. But at least after that, in a way, the story is, after you've given an initializer, you can do uncertainty quantification. So this is the point here. You can start doing Bayesian uncertainty quantification. But to do proper uncertainty quantification, you actually have to also work a bit more, because the Bayes paradigm only gives you credible sets, which might not be confident sets. But I will not go into details here. Yeah, so this overall, this should not motivate you all now to go out and use Langevin CMC for every problem you find, because this is not the point. The point is more, this is a benchmark algorithm now to prove that you have statistical and computational guarantees. And then you can compare that to other algorithms. And you actually learn something about when MCMC works and when it doesn't.
Yeah, thank you for the presentation. I have a question regarding the examples you raised, more general in terms of the Bayesian modeling. So I think during one of those slides, you said the prior part of the posterior distribution contribute to some problems of the application of the theorem. A different prior, because, for example, the basic example includes a conjugate prior, or two conjugate prior, then you can go through things. Sort of, that fits nicely with the log likelihood.
Okay, yeah, thanks for the question. It's a very good point. You could just choose a better prior, right? But in fact, choosing the prior is very essential for posterior contraction. You cannot just choose any kind of prior you want, because this is a non-parametric problem. In the end, you want to recover the theta naught, which is an infinite dimensional object. And then it's very crucial what kind of prior you choose. In fact, you have to rescale the prior, and it will disappear. This is not on the slides. No, you don't see that. So if you think of a finite dimensional problem, you don't see this. But if you think of infinite dimensional problems, this is not obvious at all. What prior you have to choose, you have to work on that. So you cannot make the problem easier or go away by choosing a better prior. It doesn't work.
I think so. In that example, you use Gaussian priors.
Yes, Gaussian priors are very popular. Gaussian process priors.
And you're saying, so essentially, it's very hard to choose a super prior.
Well, I give you one.
Yes.
I'm telling you that you will not go around the problem of infinite dimensionality by choosing a better prior. This will not go away.
Okay, thanks.
What's the mechanism behind this contraction? Is some central limit theorem-ish?
I'm not sure I will give you a satisfying answer in a minute. But essentially, the point is you have to show that the posterior puts a lot of mass around the truth. This is the first step. And then the second step is somehow that you, what can I say? In a way, it's based on the statistical model that you have in the background. You can show that having large samples yields somehow a strong contraction on the statistical properties, for instance, in terms of Kullback-Leibler divergence between the measures, and you can exploit this to say it. So you somehow show that the data looks closer and closer to the truth, but you have to use this regularization by the prior to write it down initially. But somehow this effect becomes less and less important for large data. And then you can prove with this that also the posterior puts a lot of mass around the truth. And the contraction itself, I think this is just information theoretic computation. that the measures are close in some distance, like Kullback light law, so adding a distance. Basics of Bayesian statistics, why it works. Not a miracle. It's very nice math.